In today's video, we're going to look at the second part of our exponential functions topic. So I'm going to start out this video by looking at the domain and range for our exponential functions. So we kind of looked at this with just very standard basic exponential functions, but I actually want to expand this now to look at functions of this form. So it's anything of the form f of x or y is equal to b, some value b, multiplied by a to the x plus c. So I'm dealing with this vertical stretch of b as well as a vertical shift of c. Okay, so what is my domain and range depending on my values of a and b, etc.? Well, we know that the domain of, if I have my standard y is equal to a to the x, the domain of that is all real numbers. The range of that for our standard y is equal to a to the x, we said is 0 up to infinity, but not including 0 because 0 is our horizontal asymptote. If I'm going to vertically stretch this thing, okay? It's not going to vertically stretch it downwards past our horizontal asymptote. Our horizontal asymptote is going to stay where it is, but I am going to stretch it upwards and outwards slightly using that value of b. So b doesn't actually change my range in any way. What does change it is that shift of c. So if c is positive, I'm going to move it up by c units, and if c is negative, I move it down by c units. So our range of y is equal to b multiplied by a to the x plus c is going to be c up to infinity, because c is now going to be where our horizontal asymptote is. Okay, if it's negative, like I said, we're going to move it down. If c is positive, we'll move it up. But still, that is going to be our range for this particular function. The only thing that's different is if I've got the range of this. So I've got a negative in front of a to the x. What does that do? Well, it flips our graph over the x-axis. We looked at a particular example of this in our last video. If that b is negative, we're flipping our a to the x graph over that x-axis, over y is equal to 0, which will then make the range of it negative infinity to 0. But I then have this plus c, which is then going to shift everything up by c units. So this is going to be negative infinity up to c, where again I've got that c being my horizontal asymptote, but I have taken my entire graph and it's flipped over because I have that negative in front of a to the x. Okay. We'll do a quick example just to show this. So let's say I have y is equal to negative 1/3 x plus 6. I've got 1/3 to the x that has then been flipped over the x-axis, and then it's been shifted up by 6 units. So the range of this is now going to be negative infinity up to 6. My domain is still all real numbers. We haven't changed our domain in any way. That is still all real numbers. It's just the range because we have shifted this graph. Kind of leading off of this, and we've mentioned this, given this y is equal to b times a to the x plus c, how do I find the equation of the horizontal asymptote? It's always at that y is equal to c value, okay? Whatever c is where that asymptote is. It doesn't matter if a is between 0 and 1 or if a is greater than 1. It doesn't matter if you've got a negative in front of a to the x. None of that matters. It's that shift that is going to alter our horizontal asymptote. No stretch or any value of a is going to affect that. So whenever we have an equation of the form y is equal to b multiplied by a to the x plus c, y is equal to c is the equation of the horizontal asymptote. And as I said, that stretch of b or the value of a does not affect our horizontal asymptote in any way. So if we've got y is equal to b times a to the x, our horizontal asymptote is still at y is equal to 0. It's only if we shift up or down that the asymptote is going to change. One more example that I will do here just to make sure that we're all good with this horizontal asymptote thing. If I've got f of x or y is equal to 5 to the x plus 2, okay, this is going to shift my graph to the left of 5 to the x by 2 units. Okay, so I've taken my graph of 5 to the x and I'm shifting it to the left by 2 units. My horizontal asymptote is still at y is equal to 0 because I'm not shifting up or down, so that c value is still 0. So keep that in mind whenever you do this. The next thing that I want to do is, given a graph of an exponential function and a couple of points that lay on that graph, can we actually find f of x given this graph? So we're going to be finding f of x is equal to b multiplied by a to the x plus c. So we're finding our function given the graph. How do we do that? Well, we already know that we can find c by looking at where the asymptote is. So can find c as the horizontal asymptote is at y is equal to c. So that's an easy value to find. Once we have found c, I need to find b and I need to find a. You will be given the graph and a couple of points that are on that graph. One of the points that you will always be given is that y-intercept, the point where x is equal to 0. That means that we will know the value of f of 0. So plugging that 0 value in would be b multiplied by a to the 0 plus c. Now we know what c is. And any value to the power 0, as long as it's not 0, but we don't consider a to ever be 0 anyway, a to the 0 is 1, which leaves us with b plus c. So once we know what that horizontal asymptote is, we know the value of c, and then by finding what that y-intercept is and getting that point, we can then use that f of 0 value to find b. So to find b, it will then be f of 0 minus c. So it's that y-intercept minus whatever value you found for c. Then we need to find a. And the other point that you will normally get on that graph, as we looked at before, is the point where x is equal to 1. Okay? If you get that point where x is equal to 1, plugging that into our equation gives us this. Now, if we know the function value at 1, because we know the coordinate when x is 1 and y is equal to whatever f of 1 is when you get given that graph, you know what b is and you know what c is. So now we can use that value in order to find a. So if I rearrange this, I get a is equal to f at 1 minus c over b. Okay. So let's go ahead and do a quick example of this. I'll draw out the graph and then we can go ahead and find out the equation of the graph. Okay, So this is the graph that I am given, and like I said, you are given a couple points on that graph. The one where x is 0 and the one where x is 1. You may end up with more points on the graph than this, but you need at least those two. We know already from looking at this, because of our horizontal asymptote, that c is equal to 1. So in my equation of f of x is equal to b multiplied by a times x plus c, I know that c is already 1. Now, I know my function value at x is equal to 0, and that function value is 2. So I know that 2 is equal to my function value when x is 0, which is the same thing as saying b, then multiply that by a to the 0 is just 1 plus 1. So I get b multiplied by 1 is just b and then plus 1. So I get 2 is equal to b plus 1, telling me that b is equal to 1. Finally, I need to find my value of a. And like I said, we use the function value at 1, which if we look at our graph is 7 over 6. And then if we go ahead and plug this x is equal to 1 into our formula and use our values of b and c. We know that b is 1 and c is 1. So I get 1 multiplied by a to the 1 plus 1, which is just a plus 1. So that tells me that a is equal to 7 over 6 minus 1, which is just 1 over 6. So my final formula for this particular exponential function is f of x is equal to 1 multiplied by 1 over 6 to the x plus 1. Now I'm going to look at an exponential function that is called the natural exponential function, and it's the one that we use most often whenever we look at exponential functions. It takes on our standard shape that we are used to when a is greater than 1. Goes through the point 0, 1 as usual, and I will plot out a couple more points and then we'll discuss what this natural exponential function is. Okay, the natural exponential function is the function of the form e to the x. E is actually just a constant, kind of like pi, where pi is 3.14, okay? E is approximately equal to 2.718, okay? It's much longer than that, obviously, kind of like pi is, but E is approximately 2.718. And so therefore, when I take e to the power x and draw its graph, a is greater than 1 because e is greater than 1. And so therefore it takes on this shape. It goes through the points 0, 1, 1e, okay, because if I take x equal to 1 here, I get e to the power 1, which is just e. And then when I take x to be negative 1, it would be e to the negative 1, which is just 1 over e. So they are the points that this graph goes through. It seems like a really weird number, like I said, just like pi is, but it is used a lot in different things. It's used in interest rates. It's used when we look at models for the spread of disease and how a disease spreads. It comes up in that. It's just one of those numbers that comes out in real world problems. So I know it's kind of a weird number, but it is something that we use in real world problems that we see in mathematics. So E is approximately equal to this 2.718, but we always just call it E. Okay. A lot of the time what we will do is we'll do something called a change of base. This will come up later. We won't really do it a huge amount now, but you will need to kind of know the basics of it. Sometimes, especially in these real world problems, changing the base of an exponential function so that it has this base of e is very useful. So we can have whatever base we like, whatever value a that we like, as long as it's between 0 and 1 or greater than 1. A can be any number. But it can actually be very useful in a lot of these real world problems to change that base to actually be that value e. Or to go the other way around and to change it so that we go from a base of e to a base of something that we would prefer to use. So, like I said, we're just going to do a couple quick examples here, but we'll go more into detail with this later on. And what we want to do is we're going to write each of the following as a to the x or e to the power of k times x. So the first one I'm going to look at is f of x is equal to e to the 3 times x. Okay. By the properties of exponentials and powers and stuff, we know that we can rewrite this as e cubed to the power x. Okay, when I've multiplied the powers, I can just split them up like this and take it as e to 1 power and then take it to that second power. Okay, so that means that a is equal to e to the 3, and then I can write it as f of x is equal to a to the x, where a is equal to e to the 3. Similarly, let's take f of x is equal to e to the negative 2x. Okay, same thing again, I've got e to the negative 2 to the power x. So a is equal to e to the negative 2. I could also rewrite that as 1 over e squared. And then f of x would equal a to the x, where a is equal to this number. So I've changed my base from e to the power something to a to the power x. And the last one I'm going to look at is kind of going the other way, saying f of x is equal to 21 to the x. Okay. Let's say that we want to write 21 to the x as e to the kx. Okay. That tells me that I'm doing 21 to the x is equal to e to the k to the x. So that means that 21 is equal to e to the k. We know that e is a constant, so we just want to know what power of e gives me 21. So what I'm going to do is I'm going to take the kth root of both sides, and then that would tell me what e was. You will have to do this on a calculator, and we'll learn more about this next time when we look at this changing bases stuff later on in this course. But right now, we're just I'll tell you what the value of k is, and it's approximately equal to 3.04. But whenever we do these changes of bases later on when we're solving exponential equations, this is how you're going to set this up, and then I'll show you how to solve for k. Like I just said, we will do a lot of this stuff with solving exponential equations. I'm going to show you how to solve some simple ones right now. And these will come up, like I said, later on, but they do come up a lot in things like calculus, etc. So it's good to know how to solve them. First one I'm going to look at is to solve 9 to the x is equal to 3 to the 4x minus 1. And we have to solve for x, okay? Whenever you do one of these problems, get the same base on both sides, okay? I've got a 9 as a base on the left-hand side and a 3 as a base on the right-hand side. So if I change both of those to have a base of 3, I know that 9 is the same thing as saying 3 squared. So that way I'm going to end up with that same base on both sides. Okay, so I get 3 to the power 2x is equal to 3 to the power 4x minus 1. Well, in order for those two sides to be equal, I know that the powers have to be equal to one another. And if I rearrange that, I get 1 is equal to 2x and x is equal to 1/2. Okay. Do a similar one that's very much like this. It's going to be solve 16 to the 2x is equal to 4 to the 3x minus 1. Same thing again, get the same base on both sides. So we know that 16 is 4 squared to the power 2x is equal to 4 to the power 3x minus 1. So I then multiply those powers to give me 4 to the 4x is equal to 4 to the 3x minus 1. So then I make my powers equal to tell me that x is equal to -1. The last one I'm going to do kind of leads us to some of the other exponential equations that we will solve later on. It's very similar to that. It's slightly more complicated and involves a bit more thought. We're going to solve this equation for x, okay? Not obvious until you kind of think about it and think about like terms and what we can factor out, etc. I know that e to the x is common to both terms. Actually, x times e to the x is in both of these terms. But what I'm going to do, I know that if I factor out e to the x, okay, I get e to the x multiplied by x squared plus 3x equals 0. Okay. When I've got two things multiplied by one another equals 0, I know that at least one of them has to equal 0. So either e to the x equals 0 or x squared plus 3x equals 0. Okay. If I go back to my graph of e to the x, which we have back here, as a standard exponential function, we know that it never hits that x-axis. So I know that e to the x, my function value, can never equal 0. That means e to the x never equals 0. So that means that the only possibility that I have is that x squared plus 3x equals 0. So then I can factor this to find all possible values of x. But I do not get any possibilities for x coming from e to the x, okay? Because e to the x never equals 0. It's only the other part of my factorization that can possibly equal 0, okay? And that is all due to that horizontal asymptote and that the graph never reaches 0. So whenever you get a problem like this, that looks kind of like a quadratic with that e to the x through it, what I would do is factor out the e to the x because you know it can never equal 0 and set the other part equal to 0 and solve like you would for a standard equation.